Now, what is heat capacity? Heat capacity means the amount of heat required to raise the temperature of the substance by 1 degree Celsius or 1 Kelvin. Suppose delta Q amount of heat is supplied to the substance and its temperature is raised by delta T Kelvin. Then we can say the heat capacity of the substance, that is delta Q by delta T. Okay. Now, specific heat capacity. So, heat capacity of the substance per unit mass. It implies that we can say the amount of heat required to raise the temperature of unit mass of the substance by 1 degree Celsius or 1 Kelvin. That is called its specific heat capacity. So we can write the equation of it, that is C equal to delta Q upon M delta T. Unit, that is joule per kilogram Kelvin. Now, if we think about the gaseous substance, then for gaseous substance, the amount of gas that is taken in terms of mole. So we have to define the molar specific heat capacity. So we represent it by C equal to delta Q upon mu, mu that is the number of moles, into delta T. So we can define it as the amount of heat required to raise the temperature of 1 mole gas by 1 degree or 1 Kelvin. Okay, that is the molar specific heat capacity of gas. Clear to all of you? Simple example for the specific heat capacity of the substance. Right? Suppose we have oscillator in one dimension, then it have 2 degrees of freedom, right? So we can say its average energy, that is 2 into half kBT. So that will be kBT. But suppose the oscillator is in 3 dimensions, oscillating in 3 dimensions. Then now simply we can write in 1 dimension, when your answer comes to kBT, then in 3 dimensions it will be 3 kBT. Okay. Now for 1 mole solid, the total energy, that is U equal to 3 kBT into number of molecules or constituent particles in 1 mole, that is Na, that is Avogadro number. Now Kb into Na, that is R, universal gas constant. So we can write U, that is equal to 3 RT. So change in temperature delta T will give you the change in energy delta U. As per equation, delta U equal to 3 R delta T. Now, at constant pressure, we can write the first law of thermodynamics as delta Q equal to delta U plus P delta V. But if we take the solid substance, then for solid substance, delta V, the change in volume, that is negligible one. Solid is incompressible. Okay. So we can say delta Q, that is nearly equal to delta U. Now specific heat capacity, that is delta Q by delta T for 1 mole. So we can write that is delta U by delta T. But now from this equation you can write delta U by delta T, that is 3R. So in this particular case, the specific heat capacity that we can write, that is 3R. Clear to all of you? Now here we define the molar specific heat capacity for gases, that is C equal to delta Q upon mu delta T. But experiments shows this thing at constant pressure. Suppose you want to increase the temperature of 1 mole gas by 1 degree Celsius or 1 Kelvin. Then the amount of heat required, and if we want to increase the temperature of 1 mole gas by 1 degree Celsius or 1 Kelvin at constant volume, then in these two cases, the amount of heat required for the same gas, for the same amount, 1 mole, that is different one. So for gases, we take two molar specific heat capacities. One that is at constant pressure, that is denoted by Cp, and another one that is at constant volume, which is denoted by Cv. Now we have to derive the relationship between Cp and Cv. Now see, as per first law of thermodynamics, we can write delta Q, that is delta U plus delta W. Now we can rewrite this one as delta Q equal to delta U plus P delta V. Suppose first we take the volume is constant one. Means for constant volume, let's derive the equation for specific heat capacity. Okay. Now, if volume is constant, then change in volume, that is equal to 0. So we can write delta V equal to 0. So this term will be cancelled. So we can write delta Q at constant volume, that is equal to delta U at constant volume. Now divide both the side by delta T. So delta Q by delta T at constant volume, that is equal to delta U by delta T. And here we consider the amount of gas, that is 1 mole. So delta Q by delta T at constant volume, as per definition, that is the specific heat capacity at constant volume. So we can write the specific heat capacity at constant volume, that is delta U by delta T. Say this is equation number 1. Now suppose we take the pressure is constant one. So we can rewrite the equation of first law of thermodynamics. So delta Q equal to delta U plus P delta V. But we have the equation, that is PV equal to mu RT, ideal gas equation. If we take mu equal to 1 mole, then PV equal to RT. So we can write P delta V, that is equal to R delta T. Now in this equation, we can replace P delta V by R delta T. So we can write delta Q at constant pressure, એટલે આવી રીતે સફિક્સમાં લખવાનું આપણે, બરોબર. That is equal to delta U plus R delta T. Again divide both the side by delta T. So delta Q by delta T at constant pressure, that is delta U by delta T plus R. So we can write this delta Q by delta T at constant pressure for 1 mole gas, that is the specific heat capacity at constant pressure. So Cp. So we can write Cp, that is delta U by delta T plus R, equation number 2. But here see, in equation number 1, we derived Cv equal to delta U by RT. So we can write this delta U by RT, that is equal to Cv, or take Cp minus Cv, then that is delta U by delta T plus R minus delta U by delta T. So resultantly, you will get the relationship Cp minus Cv, that is equal to R. Clear to all of you?